And now, the moment you've all been waiting for, we're going to learn why the periodic table is actually periodic. The first thing we want to do is focus on our most important term, periodic. We said earlier that means repeating. We talked about an analogy between a periodic table and a calendar, and how on a calendar you have weeks of the month. As you move down the calendar, you have days of the week as you move across a calendar. And we talked about how you notice similarities between the first day of every week, call it Sunday, whereas you really don't see a huge similarity between the first week of every month. Well, we're going to do the same thing with the periodic table, and we're actually going to discuss why this happens as we move across a period and as we move down a group. We'll start by moving across a period or row on the table. The two things that we're going to focus on are nuclear charge and shielding. As we move across a period, the nuclear charge increases. And actually what happens, we're adding, as we move over, every time we move over one atom, from potassium to calcium, from calcium to scandium, all the way across, you're always adding one proton to the nucleus. You're also adding one electron to the electron cloud. Now, the proton and the electron are, well, they have equal and opposite charges. So that offsets. You had one positive, in terms of coulombs, the force exerted by either one of them, the electron is just as negative as the proton is positive. So like we said, that offsets. What doesn't offset is that the protons are massive and the electrons are tiny. So what you end up with is two equal and opposite charges, one of which is huge, the other of which is tiny, and in a tug of war, huge wins. And I just used every ounce of restraint not to do my worst impression of Billy Fusillo, but huge wins. So when the particles are equal and oppositely charged, the larger particle wins the tug of war. The analogy I would use, and in class you'll see this, I have these really cool fired ceramic magnets that are the freakiest things you'll ever see. And I'll do a demo with a massive body and a small body. The analogy I'd give you here is between a car and a refrigerator magnet. If you had a really strong refrigerator magnet and you walked out and into a parking lot or into the driveway and you held the magnet, say 2-3 inches from the car and dropped it, what you won't see the car snap to the magnet, move over 2 to 3 inches. It's not going to do that because the car is massive, it's huge. But the magnet will snap to the car because it's tiny. So in this case, the car represents the protons in the nucleus, and the magnet represents the additional electron on the outside. The proton, wins the tug of war because it's massive. I just need to preface that before I move on. Please don't actually conduct that little demo because I really would rather not get a phone call from your parents as to why their car door is all scratched up from you trying to prove that I was actually correct. Trust me, it works. Okay, the second thing that happens as we move across a period is this concept, it has to do with this concept of shielding, which does not increase. All right, and I'm going to explain that now because this concept, not only is it a really prevalent concept with reference to the Regents exam, I mean, it's really important in terms of understanding periodicity. I got two pictures here. I'm going to focus on the picture on the right. And in the center, we said we have our protons, our nucleus. It's the attraction between the nucleus and these guys, the outermost or valence electrons that we're concerned with. And shielding is really a matter of what gets in the way of that attraction between this positive nucleus and those negative electrons. In the case of here, chlorine, what interferes with this attraction between the nucleus and the valence electrons happens to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 what we call kernel electrons, inner electrons. This attraction between the positive protons and the valence, negative valence electrons is actually screened by 10 inner shell or kernel electrons. So initially where you would think you have a charge of 17, right, positive 17 pulling on those outer electrons, these 10 inner electrons screen that out, and you end up with an effective charge of only positive 7. It's a huge difference, 17 versus 7. So what happens is, as you move across a period, this doesn't change. When you move across a period, by definition, a period has the same number of energy levels. That means the number of kernel electrons isn't changing. The number of valence electrons is. So as you move across a period, it's important to understand shielding does not increase. Now, as we move down a group, nuclear charge also increases. In fact, it increases by a lot more than when you move across a period. Instead of adding one proton, you add a number of protons and neutrons. However, this guy we gave the big star to up above, now shielding does increase. And what happens is that plays such a significant role, that screening, in determining the pull on the valence electrons that the protons are allowed to exert, that this, we say, trumps everything, to use a Euchre term. Even though nuclear charge, when you move down a group, increases by a lot, okay, this nuclear charge goes up, it's this shielding here that basically is responsible for dictating the properties as you move down a group. So these two things are both happening, but even though nuclear charge is increasing, shielding increasing is what will determine the chemical properties as you move down a group.